At full power, one engine on a single container ship can drink up to 250 tons of heavy fuel oil in one day. That's a swimming pool of fuel set alight cylinder by cylinder every 24 hours. And the strange part is that this same engine is among the most efficient piston engines ever built, turning more than half of that fuel's energy into forward motion. Most car engines manage about 30%. Power stations rarely do better than 45%. So yes, a ship nearly 400 meters long, loaded with the contents of a small city, sliding across the ocean at around 25 knots. Below decks, the crankshaft turns barely faster than the second hand on a clock, a little over 100 revolutions per minute, driving a propeller the height of a house. No gearbox, just slow and enormous torque. The engine doing that work is the Wärtsilä RT-flex96C in its 14-cylinder form, first sent to sea in 2006 aboard the Danish container ship Emma Maersk. By any honest measure, it is the largest and most powerful reciprocating diesel engine ever put into commercial service. How it came to exist is a story about global trade demanding ships on a scale nobody had built before, about engineers solving control problems that older designs could not handle, and about a shipyard fire that nearly destroyed the flagship before its first voyage. There's also a quiet rivalry between European engine makers, an arms race over horsepower, and then a financial crisis that, changed a lot of things. This is how this giant engine was built, and why its record is probably going to stand for quite a long time. To see why anyone would build an engine the size of a small apartment block, look at what was happening on the world's shipping lanes through the 1990s and into the early 2000s. Container ships were getting larger every few years, and the growth was not gentle. A vessel that carried 4,000 TEU, the standard 20-foot container unit, felt large in 1990. By the late 1990s, though, 6,000 and 7,000 TEU ships were rolling out of Asian yards. By the mid-2000s, shipping lines were ordering vessels designed to carry 8, 10, and even 11,000 containers on a single hull. The business logic was real straightforward. Bigger ship needed roughly the same crew as a smaller one. It burned more fuel in absolute terms, but the cost per container fell sharply as the deck filled up. Port fees, insurance, the salaries of officers and engineers were all spread across thousands more boxes. For shipping lines competing on thin margins, scale was the cleanest way to cut the price of moving a pair of trainers from Shenzhen to Rotterdam, or literally anywhere. There was a catch, though. The economics only worked if the giant ships kept the same schedules as the smaller ones that they replaced. A weekly service from Asia to Europe meant ships had to maintain something like 25 knots across open ocean. Slow the schedule, and the line needed more ships to cover the same route, which ate the savings before they reached the books. Speed was not a luxury. Speed was the reason this whole thing could work. 25 knots on a 400-meter hull is quite a big demand, let's say. Water resistance climbs steadily as a ship pushes harder against the sea, and the power needed to gain those last few knots grows out of proportion to the speed itself. Engines that had moved an 8,000 TEU ship at a comfortable pace simply could not push a larger hull at the same rate. The numbers ship owners were quoting to engine builders began with 80 megawatts, and they crept upwards from there. The lineage best placed to answer this was the Swiss firm Sulzer, whose two-stroke marine diesels had powered large cargo vessels for decades. Sulzer's engine business was absorbed by the Finnish company Wärtsilä in 1997, which kept the Sulzer designs, just developing them under a new badge. Through the late 1990s, shipping lanes were signaling clearly to Wärtsilä and its rivals that the next generation of container ships was going to be larger still, and that the engines would have to be larger to go along with them. What the industry was asking for in plain terms was a single piston engine that could move a floating warehouse the length of 4 football pitches across the Pacific at the speed of an old ocean liner, week after week, for about 25 years. Nobody had built one of those yet, turning a proven design into a record breaker. The engine that ended up in Emma Maersk did not appear from nothing. Its lineage goes back to 1994, when Sulzer introduced the RTA-96C, a slow-speed marine diesel with a 96-centimeter bore designed for the next wave of large container ships the company could see coming down the order books. 96 centimeters is a piston bore wide enough to climb inside. That was the starting point, though. The first RTA-96C engines went to sea in 1997, in configurations up to 12 cylinders. They worked. Shipping lines logged the running hours, engineers tracked the wear patterns, and the basic architecture proved itself across years of ocean service. And that was all very important because what came next depended on trusting the design under loads that it had never been asked to carry before. You see, in 2000, by then under the Wärtsilä badge, the engine was uprated again, and drawings for a 14-cylinder version began circulating. On paper, the bigger configuration could reach around 80 megawatts. But paper was the easy bit. The harder change came in 2003 with the shift from RTA to RT-flex. Older two-stroke diesels of this size used a long camshaft running the length of the engine to time fuel injection and exhaust valves mechanically. The RTX design threw the camshaft out and replaced it with a common rail system controlled electronically. Fuel sat in high-pressure rails along the engine, and a control system released it into each cylinder at precisely chosen moments. The benefit, in one line, was finer control, cleaner combustion, and steady running at low speeds, where the old camshaft-driven engine stumbled. Wärtsilä did not jump straight to 14 cylinders. The RT-flex96C arrived first in 8 and 12-cylinder forms, which gave ship owners and engineers real-world data on how the electronic system held up to salt air, vibration, and the rough business of crossing oceans at full power all the time. Only once those engines had logged convincing service did the company commit to the 13 and 14-cylinder versions. Stretching an engine to 14 cylinders in a single straight line is harder than it sounds. It sounds pretty hard, to be honest. The crankshaft alone grows to nearly 300 tons, and every additional cylinder adds twisting forces that try to wind the shaft up like a spring before releasing it. Bearings have to carry loads measured in the thousands of tons. The engine frame, the box of steel that holds everything in alignment, has to stay rigid enough that the pistons do not score the liners over 25 years of service. Wärtsilä engineers reworked the crankshaft design, stiffened the structural members, and recalculated the bearing loads cylinder by cylinder. The components had to survive roughly 100 revolutions a minute, every minute, for decades. By the mid-2000s, the first 14-cylinder RT-flex96C was nearing completion at Diesel United in Japan, which held the license to build the largest versions. It would weigh about 2,300 tons, stand roughly 13.5 meters tall, and stretch almost 27 meters from end to end. Its destination was already in the order book. It was that Danish container ship at the Odsent Steel shipyard, intended to be one of the largest vessels to ever float. How the slow-speed giant works. Walk into the engine room of Emma Maersk, and the first thing that registers is that you are standing in a building, not in a vehicle. The engine takes up 3 full decks. From the lower platform, you can look up past the cylinder covers and barely make out the ceiling. From end to end, like we said, 27 meters, that's about the length of a tennis court. And from crankshaft to cylinder top, it stands roughly 13.5 meters. The 14 cylinders sit in one straight line. Each has a bore of 960 millimeters and a stroke of 2.5 meters, which means that every piston travels about my height on every downstroke, 14 times over, slightly out of phase. Added together, and the total swept volume comes to roughly 25,480 liters. A family car engine holds between 1 and 2 liters. What it does with that volume is a slow-speed 2-stroke cycle, the same basic idea found in the very largest marine diesels for a century. Each cylinder fires once every revolution rather than every second one. Fresh air enters through a ring of ports cut into the lower part of the cylinder liner, exposed as the piston drops. Exhaust leaves through a single large valve in the cylinder head at the top. Fuel is injected near the top of the stroke, ignites under compression, and drives the piston down again. Turbochargers, driven by the exhaust itself, force air into the cylinders under pressure, which is what allows so much fuel to burn cleanly inside each chamber on every single cycle. The pace at which all of this happens is kind of surprising. At full power, the crankshaft turns about 102 revolutions a minute. That is really pretty slow. It's a little bit faster than a second hand, like we said. There's no gearbox between the engine and the propeller. The crankshaft is bolted directly to the propeller shaft, which is bolted to a 6-bladed propeller about 10 meters across. The engine produces its power not by spinning fast, but by leaning on the propeller with enormous, patient force every time a piston comes down. In its first form aboard Emma Maersk, that arrangement was rated at 80,080 kilowatts, about 109,000 horsepower. Later uprated versions with improved turbochargers and tuning reached 84.42 megawatts, or roughly 114,000 horsepower. The trick that made those numbers achievable at acceptable fuel economy was the common rail fuel system that defined the RT-flex generation. Instead of a long camshaft running the engine's length, opening injectors mechanically as it rotated, fuel sits in high-pressure rails that run along the cylinders. Electronic control units release that fuel into each cylinder through computer-timed valves, choosing the exact moment, duration, and pressure of injection. The same principle governs the exhaust valves. The advantage shows up most at low loads where the older camshaft engines tended to smoke and run rough. The RT-flex stays smooth and clean across a much wider range of operating speeds. Two more systems also really matter. The turbochargers, 3 of them on the 14-cylinder version, are themselves machines the size of small cars, each spinning at thousands of revolutions per minute on bearings cooled by the engine's own oil supply. And beyond the turbochargers, a waste heat recovery system captures energy from the exhaust steam after it has done its work driving the turbos. On some Emma Maersk class installations, that recovered heat ran a steam turbine and generator, producing an additional 9 to 12% of the main engine's output as electrical power for the ship. The performance figures that fall out of all of this are what really makes this engine pretty famous. Specific fuel consumption sits at around 171 grams per kilowatt hour at full load, close to the theoretical limits of what a piston engine burning heavy fuel can achieve. Thermal efficiency at the best operating point passes 50%. At maximum continuous power, the engine consumes up to 250 tons of heavy fuel a day. That is the cost of pushing nearly 400 meters of loaded ship across an ocean at the speed of a car on a country lane. Emma Maersk and the far before the first voyage. The engine that would carry the record had been to 3 countries before it ever turned propeller. The design lineage was Swiss, traced back through Sulzer in Winterthur. The development work and intellectual ownership belonged to Wärtsilä in Finland. The actual casting, machining, and assembly of the 14-cylinder version was carried out under license by Diesel United in Japan, the only yard tooled up to handle components on this scale. From there, off it went to Denmark, where it was lowered into a hull being built at the Odense Steel Shipyard for Mærsk. The Emma Maersk was the lead vessel of a class of 8 that the company called the E-Class. At roughly 397 meters long and 56 meters across the beam, she was one of the largest container ships in the world when she launched. Her nominal capacity sat at around 11,000 TEU, though Mærsk argued the real figure was higher once smaller containers were counted. She was built for the Asia to Europe run, designed to hold a service speed close to 25 knots in open water, and her single 14-cylinder RT-flex96C was what made that schedule possible. Then, on the 6th of June 2006, with the ship almost complete at the Odense yard, fire broke out. It started in the accommodation block, the tower of cabins, officers, and the bridge that sits above the main deck, and spread quickly through the upper levels. More than 100 firefighters were called in. Smoke from the burning superstructure was visible across the island of Funen, and crews fought through the night to keep the flames from reaching the lower decks, where the engine and the cargo hold sat. What was at risk in those hours wasn't just the ship. It was all the years of design work at Wärtsilä, the license-built engine from Diesel United already installed, and the flagship of a class Mærsk had bet a substantial part of its fleet renewal on. One bad night at the yard could have erased all of that before the vessel had even gone into open water. The fire was contained, the accommodation block was rebuilt at the yard, the bridge equipment replaced, and the timetable slipped only by a matter of weeks. Emma Maersk entered commercial service on the 1st of September 2006, sailing from Aarhus on her maiden voyage to Asia. The 14-cylinder RT-flex96C, which until then had existed in trade publications and engine room drawings, was now turning the propeller of a working container ship at sea. Down in the engine room, engineers moved along catwalks that ran the length of the cylinders, past covers larger than dining tables, with cylinder liners big enough for a person to climb inside during an overhaul. The engine room was heavily automated, and a typical watch was handled by a small team monitoring screens in a control room separated from the noise by thick glass. A coda came in February 2013. Emma Maersk was transiting the Suez Canal when water flooded into the engine room and the shaft tunnel through a damaged stern thruster compartment. The engine itself was undamaged in design terms, but the flooding disabled propulsion and the ship had to be towed out of the canal for months of repairs. It was a reminder of what putting an entire megaship behind a single propeller meant. One incident in one compartment, and the most powerful diesel engine ever built sat silent, waiting for the water to be pumped out and for months of repairs. For about a year, Wärtsilä had the field to itself. In 2007, with updated turbochargers and revised tuning, the 14-cylinder RT-flex96C was uprated to a maximum continuous output of 84.42 megawatts, roughly 114 horsepower, from a single piston engine driving a single shaft. But then the challenger arrived. MAN Diesel, the German firm whose two-stroke marine engines had been the main rival to Sulzer for decades, announced the 14K98 MEC7. Hell of a name, guys. The bore was 98 centimeters, 2 centimeters wider than the Wärtsilä, and the planned rating was 87,220 kilowatts. On paper, man had drawn a more powerful engine than anything turning a propeller anywhere in the world. The rivalry was not only about engineering, though. Wärtsilä represented a Finnish-led European tradition with Swiss design heritage, license built in Asia. MAN was the flagship of German heavy industry, with its own license network in Korea and Japan. Shipping lines watched the contest because the size of their next-generation vessels depended on what the engine yards could deliver. National industries took quiet pride in which builder claimed the top number. Trade journals printed comparison tables. Conference papers laid out the case for one over the other. The horsepower figure on the cover of the technical brochure was really rather important. And, well, then the market that was going to pay for all of it kinda broke. The 2008 financial crisis hit container shipping harder than almost any other sector. Trade volumes fell sharply, cargo rates collapsed, and the order books that had justified the next generation of megaships suddenly looked dangerous rather than aspirational. Compounding the squeeze, the price of heavy fuel oil climbed through the late 2000s and stayed high. A ship burning 200 tons a day at 25 knots was now burning money the operator no longer had. The response across the industry was slow steaming. Vessels designed to cruise at around 25 knots were throttled back to roughly 20 or 21, and on some routes lower still. Because water resistance climbed steeply with speed, dropping a few knots cut fuel consumption by a large fraction, often a third or more, for a service that arrived only a day or two later. Shipping lines added extra vessels to maintain weekly schedules at the slower pace, and the arithmetic of fuel saved against ships chartered came out comfortably in favor of slowing down. The consequence for engine builders was immediate. The routine demand for 100,000 horsepower under one hatch began to fade. The next generation of megaships, including the Triple-E-class Mærsk ordered in 2011, was designed around lower service speeds, twin smaller engines on two shafts, and efficiency rather than peak power. The brochure number that had mattered a few years earlier stopped driving orders. MAN's 14K 98 MEC7 never found its ship. The design was complete, the licensing was in place, and on the strength of its specifications, it should have taken the title. No ship owner placed the order, though, that would have kept the larger engine in service. The operational record stayed with the 14-cylinder RT-flex96C on Emma Maersk and all of her sisters. The Wärtsilä engine held the crown because the contest was abandoned mid-round. The cost of burning heavy fuel. Now look, even at the efficiency the RT-flex96C achieved, 50% of the energy of 250 tons of fuel is still a lot of carbon and sulfur going up a funnel each day. Burning that much of anything has consequences, and the fuel in question made the consequences worse. Heavy fuel oil, also called bunker fuel, is what comes out near the bottom of the refining process. It's the thick, tarry residue left after the lighter fractions have been drawn off of petrol, diesel, and jet fuel. It is cheap by the ton, dense in energy, and viscous enough at room temperature to behave more like cold treacle than a liquid. Before it can reach the cylinders, it has to be heated to around 130 degrees Celsius in tanks and pipework, separated from water and sediment in onboard centrifuges, and pushed through filters fine enough to protect the injectors. Historically, it also carried sulfur content of up to 3.5% by mass, figures unimaginable in any road fuel. Shipping's share of global carbon dioxide sits at roughly 3%, and through the 2000s it became clear that the industry's sulfur oxide and particulate output, concentrated along busy coastal routes, was contributing to respiratory illness in port cities and acid deposition far inland. The RT-Flex's electronic injection helped at the margins: cleaner combustion, less smoke at low loads, slightly less specific consumption. But the basic chemistry of that fuel basically meant that it was going to be dirty, no matter what. The regulatory response arrived from the International Maritime Organization on the 1st of January 2020, with the global cap on sulfur content in marine fuel dropping from 3.5% to 0.5%, with stricter limits already in force in designated coastal control areas. Operators of ships powered by engines like the RT-flex96C had three practical paths. They could fit exhaust gas scrubbers, large washing towers in the funnel that strip sulfur from the exhaust with seawater. They could switch to very low sulfur fuel oil, a more refined and noticeably more expensive product, or they could move to marine gas oil, cleaner still, but pricier. Most of the E-class ships had scrubbers retrofitted, which kept them on the cheaper heavy fuel while meeting the new limits. Wärtsilä built a parallel response into the engines themselves. Electronically controlled cylinder lubrication fitted across the RT-Flex feet metered oil into the liners only when it was needed, cutting cylinder oil consumption by a meaningful fraction over a voyage. The later FuelFlex ICU upgrade reworked the fuel injection control units to extend service life and reduce the small leaks that had built up across years of running. All of which raised the bar for the people running the engine room. A senior engineer aboard an Emma Maersk class ship had to read electronic control diagnostics, manage high-pressure hydraulics, supervise fuel heating and centrifuging, interpret continuous monitoring data, and still understand the heavy mechanical guts of a slow-speed two-stroke when something needed to be taken apart at sea. The last giant of the diesel age. In 2015, Wärtsilä sold its two-stroke engine business. The new company was called Winterthur Gas and Diesel, headquartered back in the Swiss town where Sulzer had built large marine engines for more than a century. The majority stake went to CSSC, the China State Shipbuilding Corporation. The Finnish badge came off the largest two-strokes, and a Chinese-Swiss venture inherited the design archive that had produced the RT-flex96C. The trajectory traced by that single product through 3 decades is most of the story of modern shipbuilding in miniature. The bore lineage was Swiss, the development Finnish, the 14-cylinder castings Japanese, the hulls they sat in came out of Danish and Korean yards, and the company that now owns the drawings answers to Shanghai. The engine that moves the world's cargo, assembled by cargo from all over the world. Through the 2020s, the 14-cylinder RT-flex96C still holds the record as the most powerful, reciprocating diesel engine in commercial service. Many remain at sea, aboard the Emma Maersk and her sisters, with overhauls keeping them running well into their 3rd decade. And that record may stand for a long time, because the question engine builders are now asking is a different one. Orders are going to dual-fuel designs that burn LNG or methanol alongside diesel, to ammonia trials, to hybrid arrangements with battery support, and to hulls drawn around lower service speeds. Raw horsepower is no longer the hardline figure on the brochure. The RT-flex96C arrived at the last moment when it could have. Container shipping wanted larger ships and faster than anyone had built, and Wärtsilä's engineers delivered something that turned more than half of its heavy fuel oil into forward motion at 102 revolutions a minute. It was the high watermark of the big oil-burning diesel age. The record may last, not because nobody can build a bigger one, but because the prize the industry is now chasing is moving the same cargo with less left behind in the air and the water. Thank you for watching.